Hello viewers, question 6. We have a system in equilibrium here, which means that the resultant should be 0. And we need to find the two forces F1 and F2 that make that the case. So let's draw our force table. We've got the forces, we've got a horizontal component, and we have a vertical component. So let's start with F1. As it's pointing exactly upwards, horizontal component is 0, and the vertical component is F1, which we are looking to find, just like we're looking to find F2. So the horizontal component of F2 is F2, since this is a horizontal force, and that makes the vertical component 0. F1 is pointing upwards, F2 is pointing to the right, so both of those are positive. Now for the remaining force, which is acting 39 degrees from the vertical on the left, below the horizontal, we need to consider that right triangle there, and we need to work out what its horizontal and vertical component are. For the horizontal component, we are looking to find the opposite side, which is, we know the hypotenuse is 15, so we've got the hypotenuse and the opposite. We're dealing with sine, angle is 39, and its size is 15. As that's pointing to the left, it's negative. And for the vertical component, we're dealing with the adjacent side, the side connecting the angle to the right angle. Adjacent, and we know the hypotenuse is 15, so this will be cosine of 39. It's going to be 15, and it's going to be negative since it's pointing downwards. So since it's in equilibrium, the totals should be 0. So we've got a total of 0 in the horizontal direction and a total of 0 in the vertical direction. Okay, so if we look at the horizontal column, that means that F2 minus 15 times sine of 39 equals 0, and that means that F2 equals 15 sine of 39. Calculating that, we get 9.44. And for the vertical column, we've got F1 minus 15 cosine of 39 equals 0. So therefore, F1 equals 15 cosine of 39. And if we calculate that, we get 11.7. So F2 is 9.44 and F1 is 11.7. We could have also done this using a vector triangle. So let's draw a vector triangle to convince ourselves that this is the case. Let's do it another way. So F2 is a horizontal force. If we draw F1, so it's nose to tail with that, so in other words, drawing F1 starting from the head of F2, so those two are nose to tail, as they should be when you're drawing a vector diagram. And then we need to draw the 15 Newton force nose to tail with F2. Since it's in equilibrium, these three vectors should form a closed triangle. So this hypotenuse is 15 newtons, and we've got an angle there of 39 degrees. That's a 90-degree triangle. If we apply SOHCAHTOA, sine of the angle, sine of 39, equals the opposite, which is F2, divided by the hypotenuse, which is 15. So therefore, we get the same conclusion. F2 is 15 times sine of 39, which we've already calculated to be 9.44. And for the cosine case, cosine of 39 equals the adjacent, which is, this is f1 over 15, so therefore f1 equals 15 cosine 39, which, as we calculated before, that was 11.7. Thanks for watching. Over and out.